So, all right, thanks everybody for the feedback. I did make some changes to make the list example easier to understand. So it's now specialized to int. It's just int list f of a, right? There's not the two type parameters. There's not the confusion of having fmap over the second type parameter instead of the type the list is parameterized over. So again, I'm just going to run through the catamorphism example like really quickly again. So you have int list of f where the recursive parameter is a. That's the subsequent list. That's like the next part of the const cell. And you have an int list, which is just a fix of, int list f, not list f. And you can see the same example sort of situation. Still works, because I used int for everything. It didn't need to really be parameterized. So let's look at catamorphism again, right? This time I've specialized f to int list. So int list f. So, that's just going to curse of thinking I can do that. Right. So we're turning an int list f of a into an a, right? Sorry. That was a classic example of hubris. Right. So you can see here, with it specialized, hopefully this should make a bit more sense. So you start with a fix of int list f. You turn it into an int list f of fix of int list f. This should be int list f. And you get an int list f of a. And then you collapse that down to an a with this, right? Does that make a bit more sense? Because then you have the f map over the int list f of a. So here you have an int list f of fix of int list f. You collapse that down via the f map to collapse this bit down into an a. And then you finally apply the algebra to that to get an a, which is all we really want from life, getting a's. No, school's over, sorry. But yeah, so again, the two-list algorithm here, parameterized over int list, gives you a list of int, right? You just apply the catamorphism to the algebra, and the algebra just takes an int list f, where you assume that you've turned all the recursive parameter, or all the, everything that's below the current level into a list of int already, and then you just have to work on collapsing a single layer down to a list of int. So again, you hit the nil case, nil, that just gives you an empty list. That lets you stop chaining f maps, and then you just sort of collapse down from there. Because you'll have const cells before that, you just take the x and you prepend that to the accumulator, which is the everything you've already handled. Right. Was a yes, inline coding is definitely easy, so we're just going to do inline slide editing because that's cool. Right. So catamorphism, you're just sort of doing a fold where you collapse each layer down. Anamorphism, that's an opposite of that. That's an unfold, right? So you're starting instead of starting with like a fix of int list, you're starting with just an a, right? And then from that a, you unfold a single layer, which is an int list f of a, using this algebra, which gets you from a to int list f of a. So that unfolds just a single layer, right? So let's actually look at this, but with, that's the joy of having this here. So let's say we start with 1, 2, right? So first, what we're going to do is apply the algebra, and that consumes, let's actually look at the definition for that first. Right, from list, right? We're taking an int list, or taking a list of int in the Haskell sense, and transforming that into sort of our bespoke int list type. And what that looks like is a function that goes from a list of int to an int list f, which has an extra type parameter. This was a horrible idea, sorry. I hope this does make it a bit more clear. Yes. And just you're keeping the list of int. That's like sort of the seed from which you unfold the int list f. And you're just removing something from it. You're taking the head of the list, if it matches that, and you're building a con cell with the remaining list being the next part of the con cell. And eventually you'll hit the empty list case, and that corresponds to nil, which is sort of the dual or the reverse of the thing that we were doing before. So yes, let's look at what this looks like in practice. So first application of the algebra is you're just going to go from this to cons 1. This goes here. And then the rest of the list, it's more like this goes here. And then you fmap over this con cell, right? And then you apply the same function to here. You'll get cons 2, and then you hit an empty list, right? So you fmap over that again, you consume the empty list, you just get nil. That gives you your full list. And we're just going to make sure these round trip in sort of a sanity check way by hopping into the REPL. And it's, yes, this is the previous version that still uses the parameterized list, so it's defaulting to integer, which is what we're doing here anyway. You can sort of see that we go to our list f type and then back to a Haskell list. So sanity check, right? This does round trip. Right. So we can also just do essentially the same thing, but monadic. Which I'm not going to, sorry. So a couple of these say int list instead of int list f. This should be int list f. This should be int list f. Ditto all of these. Sorry. I hope this does make it a little bit more understandable, parameterizing it over int list instead of list f. I just did that on the fly. So here we're just doing that in a monadic context, and we're using traverse instead of fmap to recurse into the structure. So this has a couple different things, right? We can't take advantage of Haskell laziness here because we're actually doing a monadic action over each. We're not just doing something that can be short-circuited if we don't expand the thunk. So normally you would be careful about doing this because if you have an infinite structure, and fixed point is very good for expressing infinite structures, like a stream, for example, you would actually just hang because you'd be running a monadic action over every stage of the infinite structure, which is generally not recommended. So this is just doing the same sort of actions. You're first unfixing it, you're unwrapping it to get your like int list f of fix int list f. Then you have, you traverse over that with kata m alg, and you collapse the inner layer down to just a. And then you have your algebra, which you just apply to the int list a to get you just an a in a monadic context. So we can have a simple example with that. And we're just printing every element in a list, right? This is fairly simple. Let's actually just run this over like 1 to 5 or something. And you can see here, it actually is traversing it. So it's going in reverse order because it repeatedly stacks those traverses until it gets down to the last elements. It traverses all the way in, and only after it finishes all the traverses does it hit the algebra on the outermost element. So that's why it is reversed. There's also a monadic anamorphism. We're not going to dwell on this too much. It's sufficient to know it exists. Essentially, if you have some function that in a monadic context unfolds a single layer of a structure, you can sort of apply that to itself recursively to build up that entire structure from a seed value in a monadic context. So this has been a bit baffling. Recursion schemes. There's a reason this was in the advanced track. Very glad I did that. But let's get back to why we care about this, right? Let's get back to how this helps us in like a concrete system where you can actually build things. This is how it's going to apply to directory layer. So you have a functor instance for this, just to recap. The functor instance for file tree entity is you just map over the A, and the functor instance for dir layer is for each file tree entity in this like list of tuples, you map over the file tree entities A, which should make sense, right? And then you can just stack a bunch of directory layers inside a fixed point to get a arbitrary recursive depth directory tree. Quick break for questions. Does this, even if you couldn't like re-implement recursion schemes, does it sort of make sense how you can like do that with functions that can fold or unfold a single layer? I linked a really good recursion schemes tutorial, this blog post in the Yoneda. If we can just assume that we have some magic called recursion schemes that provides these function definitions and lets us do things with them, I'm going to get back to why we should care about that, right? So once again, right, we have catamorphism. It's magic. It just lets us take a f of a to a and a fix of f and collapse that down to an a. So again, hash layer gives us a directory layer where it's parameterized over the hashes of the subsequent layers instead of having the recursive links. So we just we take that, we ASON encode it with the subdirectory links just being hashes, and then we just hash the resulting byte string. So all we really need to do, given that, is just to provide that to catamorphism and run a hash over an entire directory tree. And that just works, right? That gives us the hash for the entire thing. It starts from the leaf nodes, which don't have any recursive parameters, so we can stop computation there. It hashes the leaf nodes, and then it rolls those hashes up so that we can hash the nodes that actually have hash pointers. Right. Second cool thing we can do with this. We can write a directory tree to the disk. Let's actually, yeah. So look at this in detail, right? So we have a base directory. That's just where we're dropping the hash keyed files, the hash keyed JSON encodings of the directory layers. And we just do that for each layer, which is having every recursive link substituted with hashes. And then we just return the hash inside of IO because we're doing an action. Yeah, so again, you just pipe this into cata m. You have the monad being IO, and you have the traversable f being the directory layer. And then you just take your single function, fa to m of a, which is sort of the magic thing from before. And that's actually just our directory layer of hash to IO of hash, right? You have to provide the base directory here so that it's of the right type. And then that just sort of folds it up the entire tree. It'll take the leaf nodes, it'll encode them as JSON, it'll write them to a store using the hash as a key. Then it'll give you the next layer with just the hashes, and then you hash that. You write that to the store, you return the hash of that, and you keep going until you have the entire tree. Right. Does this make like a bit of sense? Does anyone have any questions? Yes.
You said in the monadic style of kata, it will load the whole tree.
Yes, it'll run over every branch of the subtree. And if you have an infinite structure, you can imagine like you have a fixed point of like a stream where there's no nil case. So that you wouldn't be able to run a monadic catamorphism over that because it would never terminate. Probably. We're not using that here.
Are you aware of any possible like kind of streaming solutions for doing this sort of thing? I mean, it's kind of tough to imagine with the directory tree, I guess.
So yes, what you can do is you can do a catamorphism that builds up an IO action as it traverses subsequent layers. And that way you can short circuit or you can do whatever. You don't have to like strictly evaluate the tree because you have control over the monadic action production instead of having the monadic bit be baked into the thing that recurses for you. So you can't actually build up like lazily actions that you run in sequence. And that would actually run the action from the outside in instead of vice versa, or really however you want to, because you would have control over like what order you do the traversal in, for example. Whereas with kata m, the order of the traversal is sort of just encoded in the traversable instance. Yes. And again, you have the monadic anamorphism. That's just sort of equivalent to the monadic catamorphism, except you would use it to read a layer, to turn reading a single layer, which is just, ASON. That's just decodes, given a file path, given like some ASON instance, it decodes the thing of that file path, attempts to give that to you. And this is fairly simple to write. You just go from a hash to an IO, a monad of a directory layer of hash, and then you just pipe that into a monadic anamorphism, right? A monadic unfolding, where you unfold from the top down, like you unfold the first layer, like you'd read the first layer from the file tree store, and then for each hash link in that, you would then pass that back into this, read those layers, and keep going until you hit a terminating case, like something that just has file entities and no more subdirectories. Yeah. So that's I think that's like a little bit of motivation for using recursion schemes, because read layer, write layer, and hash layer are just sort of things you want if you're working with Merkle trees. Like, it's a natural formulation for working with Merkle trees, and then you can sort of plug it into these magic abstractions and get some useful tools out of it. There's actually an hour after this talk where there's the intermediate and everything run for another hour, then there's lunch. I would be really happy to go over recursion schemes, any exercises, any questions with anyone in that time, because it is kind of hard to fit it into an hour. But, that's, yeah. Right. Before we get into diffing two directory trees, which is kind of the meat of this, any more questions about recursion schemes, read layer, write layer, any requests to show things in the REPL would be very appreciated. Cool. And seriously, I want questions. It's a sign more of me discussing something than a sign of you not getting something, so questions are appreciated. Right. I'm actually going to make this slide a bit bigger. Some of the other ones will need to use the full screen, but yeah. So, diffing two directory trees, right? Here's some of the cases that we're going to have. We could, you could imagine you could have more branches to this sum type, but this is sufficient for this. So you have like a file has been modified, you have a file has been replaced with a directory replaced with a file, an entity deleted, an entity created, right? If you have a directory tree A that has something, directory tree B doesn't, that's a file deleted. If just a file contents change, it's file modified, etc., right? So what we're going to want to do is we're going to implement something that takes two directory trees, right, and gives us a list of tuples of the path at which a diff is and the actual diff. So this is as now undefined. We're going to implement this. And this is going to be just sort of a proof of concept that we can diff two directory trees. It doesn't do the lazy traversal, and it doesn't do the short circuiting based on hashes. That'll be added in session 3. But this is just sort of a proof of concept that we can write that algorithm over the structure in a sort of elegant way. Fingers crossed, already the elegant part, but I do think it is. So let's look at all the cases. Like, we know we're going to have a couple cases, three broad cases, right? We have two trees. The first two cases that are simple are an entity exists in the first tree, but not in the second tree. We call that entity removed, right? Because it's been removed from the tree between the two diffs. And that's on removed, where we have it at a single file path. We have a file tree entity with the recursive link just being directory trees. This is the fixed point version with just the file tree entity instead of the full directory layer. And we produce, as with diff-dir trees, we produce a list of file path and diff tuples. So if it's removed, super simple, we just look at the path, and at that path we have an entity deleted. And if it's added, at that path we have an entity created, right? This is not the interesting case. This is the interesting case. So handling conflict, which as always is the interesting part. If you have, so at a single path, at a single file path, you have two file tree entities, and they're different, and they're potentially different between the two branches. Like a subdirectory or a file exists in both branches. So what do you do then, right? You have a couple cases. Right. So simple two cases. You have a file entity in one branch and a directory entity in the other. Got a file replaced with a directory. You don't keep going. You don't traverse that. It's just different entity types. Ditto for here. If it's a directory and then it turns into a file, it's a directory replaced with a file. You stop there. You tag it with the path. You return that. That's the only diff there. Cool. So this, if you hit two files, you just actually compare the files structurally. If they're not equal, you have a file modified. Otherwise, there's no diff. In like the fully worked version of this, you would be comparing file hashes, which would just be like convenient and quick because they're a fixed size hash. Here, you're comparing the file bodies because, as I said before, you have inline strings in this for simplicity and fitting in slides. Right. The more complex case, the case where you have to recurse, is if you have a conflict between two directory entities, between two subtrees, right? So you have subtree A and subtree B, and they're at the same path. They're at path, right? You don't know if they're equal. So currently, we don't have the cryptographic hashes inline. We just know how to fold something all the way up to get the cryptographic hashes. So we're not able to short circuit based on that. So what we do is we just recurse with diff dir trees, D1 and D2. And the file tree entities are actually backed by directory trees, so we can just go back to that stub we defined before. And then we just fmap over the resulting list because we have the file paths there, right? We update path, we just prepend the path of this because any diffs that result from this are at this path. Does this make sense so far? Quick break for questions.
Are we calling the function we are in recursively? I mean, diff trees is this the function we are implementing currently?
Yes, we have diff dir trees is currently just a stub of type dir tree to the list of diffs at file path.
And in the next slide, we call this function recursively, which kind of defeats the purpose of recursion schemes.
Oh, yes. This doesn't fit into recursion schemes. The diffing doesn't, because you sort of have to zip two directory trees together. And you can't zip two structures together generically, as far as I can tell. I would be very interested if someone's figured out a way to do that. But basically, this is as close as I could get to that, right? Because you have to know the actual structure of it to zip the two together. And that's what we're actually going to get into on the next slide. So this is, you can do a lot of the simple stuff, like grabbing a structure from a store given just a hash and writing a structure to a store and getting a hash. Like, those just give you a lot of the primitives you need to actually work with this. But for diffing, you do actually need to sort of manually go down the tree of fixes, the tree of fixed points. So that's why I did feel like the need to actually go a bit into how the fixed point is implemented and how you work with it, just so you can sort of see this stuff. But you're exactly right. This is, it's going to dovetail with the recursion scheme stuff in the next session when we add the laziness and when we add the hash-based subtree short-circuiting.
And
but
then we won't be doing direct recursion in our
right. It won't be direct recursion because it has to zip the two together. And as far as I can tell, you can't zip the two together without knowing about the specific structure of the F. Like, you'd have to write a zip function that somehow abstracts over the idea of zipping two structures together.
The align type class for that.
Okay, I really do want to hear about it.
Write the instance for it, so.
Right. So here's actually how we like sort of tie the knot, right? Because so far, all we know, oh, sorry, let's.
Can we have the return type to be also a tree? Because when you give two trees, it would be nice to have a tree of diffs, basically.
Yes, that's actually what I do with the merge function. I mean, you could do that. Yes, you could absolutely do that. I'm not doing it here. I think what you would do is you'd annotate every level with a diff. But for one thing, it's like really hard to print out like recursion schemes tree as, I mean, you can, right? You can define a catamorphism with like a pretty printer or something, but it's much simpler to get like a list of tuples that you can trivially show in the REPL. Yes, you can absolutely do that. Anyone else while I'm stopping here? Cool. Yes. So, okay. So just to recap, we have handlers for the case where something exists in the first map but not the second, and in the second map but not the first. And we have a handler for something where something exists in both maps. So we need to actually merge the maps and work with that. So fortunately, we don't need to do any work for that because data.map.merge handles literally all of that, because if we have a list of key and value tuples, that's basically just a Haskell map, right? We can convert that to a map in Haskell. And then we can just merge those two maps and provide a handler for all those three cases, and we're ready to find those handlers. So this is what that looks like, right? We have to actually define diff-dir trees at some point. You can't really have undefined in your code forever. So you take the, yeah, that should be dir layer, sorry, and not dir. It should be, oh, I have it in the REPL. I forgot to copy paste this from the REPL. Sorry, let me actually just show you that. Right. So you take a fix of directory layer, you look at the entities in there, which is just a key value tuple list, and you have the fix of the second directory layer, which is ditto. So all you really do is you have a map, you convert those both into maps, you merge the two maps, you handle the case where something's missing on removed, the case where something's missing on added, and the case where you're zipping two together, where you have a single path where it exists with entities in both maps with on conflict. And you have those down here, right? On removed, on added, same type. On conflict is the same as this, file path, file tree entity, dir tree, except there's two file tree entities because you have something that exists in both maps. Now this gives you a map of file path and then the actual result that you care about. And to your question, right, if you wanted to reconstruct a tree from this, you would take this map and use the file path here. But what we're doing is sort of short-circuiting the map, because we really just care about the elements in this case. So you grab the list of elements from the map, you get a list of these things, and then you just join the list using like the list monad. I'm just going to show you some examples now in the REPL, like to convince you that this works. While I get those queued up, does anyone have any questions? Cool. Either that means everyone is stumped or people sort of get it. And if you're stumped, I would really appreciate it if you come talk to me later. I will do everything I can to help make this make sense. So let's make just a temp directory, right? And it's got foo, it's got test. You can sort of see that here, right? So we're gonna use a function that I haven't really introduced yet, but we're just gonna like look at it really quickly. This is just a anamorphism that unfolds by reading from the file system, and it's just what we're using to actually read trees. So I can show you examples that interact with the directory structure instead of just using artificial stuff that I've constructed in a REPL. Yes, read dir tree. Sorry. Yeah, read tree. So this is going to be the first tree, is just everything that's at Merkle scheme/temp, being like bar.hs and test. And then we're just going to call that tree 1. Yeah, so some changes, right? Let's like create something inside test. Test/baz, it's the standard metasyntactic variable. And we're going to modify bar.hs. We're going to add foobar to it because it's thinking of strings on the fly is hard. So we've changed both things. Test is the same, right? But we've added an entity inside it. So this is just going to be called T2, right? And we're going to diff T1 and T2. As expected, oh, did I actually change? Yeah, sorry. Oh yeah, so we created that entity, and I think I like left the read it until a bit too late there. Yeah, but let's actually modify that again. Yes, so now we actually do get the file modified. Let's say we replace, we remove test and we create a file called test. We'll get, directory replaced with file. We can do that reversed. So this is like basically fine for a really small temp directory sort of situation, but it gets really problematic if we have a large repo because there's no short circuiting here, right? This function has to actually go through the entirety of every tree, and it has to zip the entirety of them together and compare everything, right? We really don't want to do that. So over the next session, Friday, we'll be showing you how to make these trees lazy so that you only have to read from the store the absolute minimum required. We'll be adding print line statements because that's my favorite kind of debugging, just to prove sort of that we're only looking at the subtree bits that we care about. And we'll also be using the cryptographic hashes to avoid having to traverse bits of the tree that change. So like, let's go into a bigger repo, right, to sort of make sense of that. Yeah, so this is the actual Merkle schemes repo. Let's actually, yeah, HGit. That's the one where I actually have the fully worked version of this. It also has like a Merkle tree for the commits. It has hashed blobs instead of having the blobs inline, which is non-performance. So we're just going to load that. Yeah, so I just diffed T1 and T4 here. So you have a file modified with bar, and I modified that twice, so you don't get two diffs for that. And then you have for test, directory replaced with file, because I nuked that and replaced it with a file. Does anyone else have any requests for like, I have the temp directory up, I can like mess around with it. Basically, if you want to poke at this and like, how does it handle this case or that case, I can do that now. Please no symlinks, by the way, it doesn't handle symlinks. No hands, cool.
What about permalinks?
Also no. Really just files and directories. Also not sockets. So let's just like to show that it doesn't completely fall over when running with a larger directory, we can just run it on this. And it does ignore everything that's prefixed with a dot, so we're not going to descend into like stack work or something, which would just be, no one wants to do that. Because that is not human readable directory. So here you have this thing. Oh, I already created a bar.baz in there, so let's delete that. No one ever names a good file bar.baz. Yes, now we're back to the master state. So we can, show that this works with a large directory tree. And yeah, we've deleted bar.baz. And just for fun, let's drop this into, let's actually hash this. And we can traverse it and hash it pretty quickly because it's just in memory. It's SHA-256. That's, one imagines, fairly optimized because I got it from Kryptonite, which is seems to be the canonical cryptography library for Haskell. Right. So we have 15 minutes. I really did not expect to get through this fast. That might be because I blazed through stuff too fast, left people confused. So what, do people have any remaining questions? Cool. Let's actually, you were asking what it would look like if you're using a tree instead. So let's actually look at what like the merge function looks like in HGit. And yeah, this is the lazy version, right? This is kind of cool because you don't even need to know what monad you're running in. The act of constructing a lazy directory tree, which is pure, right? It's a pure function, doesn't do any actions. You only have to do actions when you dereference layers of it from the store. Gives you some lazy Merkle directory, but it's parameterized over M, right? You don't need to know what that M is. You just need to know that you can sequence actions in it. And it gets you just like a lazy Merkle directory again. So you take two trees, you mash them together, you get an output tree. Instead of taking two trees and mashing them together and getting a list. This is a bit. We'll go through that. We'll go through that Friday. It's a bit more complex, but that does exist. It is quite natural because you're constructing a map, and you can easily go from that map back to a list of key value tuples and use that to rebuild a tree as you fold through it. Yes. I really didn't expect to get through this with extra time. I have more slides for Friday, but it seems better to wait for Friday for that. We can go back over some recursion scheme stuff. If anyone, I can diagram some stuff out there.
Yeah, so we've only covered anamorphisms and catamorphisms. It begs the question about hylomorphisms and their nice
future morphisms, yeah.
Well, that would also be nice, but yeah, basically kinds of morphisms and their usefulness.
Oh yeah, there's like a whole zoo of morphisms. Catamorphisms and anamorphisms are just some of the basic types that do folds and unfolds. If you want to like do a fold that can look at all the structure of the previous folds, you can do recursion scheme things for that. You can do all kinds of stuff with that. We're not doing this here because just catamorphisms and anamorphisms are kind of hard to explain in like 30 minutes. So I don't want to get into like the whole zoo of stuff that you can do with recursion schemes, but that is a very good point. You get this like large library of abstractions that you can just work with in interesting ways, your recursive structure, and you don't need to like sort of roll your own abstractions each time. I linked some type of way, SUM, in the Yoneda thing. It's really, it's how I learned recursion schemes. It's how I finally got them to stick. I'd recommend going through it. If you have any questions, like on going through the first couple. If you want to get to hylomorphisms, you can go through the whole thing. But if you go through it, if you have any questions, please find me. I'd be really happy to help you work through exercises and stuff. I really do think this is interesting. I think it's worth learning about, and it'll, like, if you want to do compiler work, for example, if you want to like take an AST, like an abstract syntax tree, and say fuse multiple passes over it into one pass. Recursion schemes lets you do that. It lets you annotate every level of an AST with, say, the type of that node in a way that's just like very elegant. It's like, I know some people who I work with who I learned about recursion schemes from, who sort of come from like a compilery background, and they were just singing the praises of this stuff. So I thought I had to learn it and sort of applied it to this. But it's really very generic. You can use it with any recursive structure. It doesn't really need to be a tree. It can be like, I mean, a tree is the canonical recursive structure, so it'll probably look something like a tree. But yeah.
Might be worth mentioning also all those weird zoo of combinators and stuff can actually be implemented in terms of kata and ana.
Yeah.
So if you have kata and ana for your data type, basically you can implement any of those other.
Right.
At the same time, you'd probably prefer to implement kata and ana in terms of Hylo, because that's more performant. I think so, because Hylo allows you to fuse multiple morphisms. If you've done
Hylo is the one where you unfold and then you fold, right?
Yeah,
At the same time? Oh yeah, that one would be more efficient probably. If it's like futuromorphism or histomorphism, not really, I think, because it'll be about the same.
Sorry,
Yeah.
be more performant.
Maybe worse.
Okay, before we get into this, right, I'm just going to give the pitch for the next two talks, and then we can break out into a discussion group. Awesome. So things we're going to add: lazy traversal of Merkle trees, which is sort of key to like working with them in practical distributed systems contexts. The sort of hash short-circuiting comparison, where you actually annotate each level of the tree with the hash. And the lazy traversal, you'll also be interleaving an I/O action with each level of the tree. And then finally, you'll get some generic versions of directory tree specific functions that you can use if you want to prototype your own Merkle tree-based system. Like if you want to build your BitTorrent clone, if you want to build like something like Unison, if you've heard of that, where it's like an AST that's like Merkleized, you could use this. Yeah, actually, yes. You'll get some cool abstractions out of this. And I actually want to show you something on GitHub pages. Let me see if I can pull it up real quickly. Yeah, anyway, I'll post a link to this later. I actually have a directory tree and commit graph viewer that I built in GHC.js that traverses a structure as like sort of used by this. It's like, it was actually quite easy. It's like sort of a proof of concept that you can use this as a way of working with like distributed systems and like actually building something you can step through. Yes, I'll post a link to that in Yoneda soon. It's we've got about 8 minutes left, and I really don't want to like try and reconstruct the URL tree, but I will if I have to. Let's see if I can do that.
So you need both this and this.
Yeah, I'll post a link to that in Yoneda. Finally, thanks so much for coming to my talk.